Welcome to chapter 9. Here we're going to talk about alkynes. This will be very, very similar to our discussion of alkenes in chapter 8. The only difference is now we're going to have two pi bonds instead of just one, right? So the alkyne functional group is going to look very similar to what we saw before. Now, there are two different types of alkynes that we can see. If that triple bond is sandwiched in between two R groups, they can be the same or they can be different R groups. But if it's in the middle of a molecule, this is what we call an internal alkyne. And if that triple bond is at the end of a chain, that is what we call a terminal alkyne. We use this terminal and internal discourse also with understanding double bonds and functional groups and things like that. But it's really important to know it here because what we're going to see in just a little bit is the acidity of terminal alkynes. And the only time we have that acidic factor in the alkynes is when that triple bond is at the end of a chain, when there's actually a hydrogen on one of those groups rather than two carbon groups. So just a couple of refreshers. The carbon-carbon triple bond itself is linear, right? So we can think about the bond angle for any of these would be 180 degrees. That carbon is sp hybridized, sp, all of them. And so what we can start to think about is that is the shortest bond. The carbon-carbon triple bond is the shortest that we have. It is the strongest in terms of bond dissociation energy for the triple bond. And it is composed of two pi bonds and one sigma. That's what makes our triple bond itself. It's not 3 times as strong as the single bond, right? But it is stronger than the single or the double bond. And so what we're going to first talk about is looking at the shape. Remember that with the 2 pi bond aspect, we have 2 p orbitals that are parallel and overlapping. Notice those 2 hydrogen or 2 electrons. Let me just highlight them here. Here's one pi bond. Here's the other pi bond, right? So there are 4 electrons in pi bonds, and there are 2 electrons in the sigma bond, right? So the sigma bond is a carbon sp to another carbon sp, and the 2 pi bonds are the p orbitals. And remember that they are 90 degrees from each other, right? On the perpendicular there, 90 degrees. That's going to be important for when we start talking about reactivity. We just want to remember this 3-dimensional shape that is linear. All right, just again, some basic properties. When we look at the alkyne, why it's important, why it's really getting a huge focus here in this chapter is because there are some basic properties that we can think about. Specifically, what I wanted to jog our memory of was S character, right? And that S character is important specifically when we talk about acidity, right? So in all of these carbon to hydrogen bonds, we can identify a pKa for these. And remember the factor that was really important to understand the difference in pKa is because of the difference in hybridization. And therefore, when we start looking at these pKa's, we see that the alkyne has a relatively low pKa compared to the alkane, ethane over there on the left-hand side. sp3 hybridized carbon to hydrogen has a pKa of 50. Very, very stable, very unreactive. Ethylene, the carbon-carbon double bond, right? The sp2 carbon to a hydrogen is very close. It's a 10 to the 6 times more reactive than ethane. However, look at acetylene. Acetylene is the common name for the alkyne we see there with 2 carbon, C2H2, and the pKa drastically drops. And that is primarily due to S character. Remember, the s orbital is lower in energy and is smaller. So when we think about the shape of those hybrid orbitals, the closer you are to the nucleus for those electrons, the more stable those electrons will be. And so there is better stability in that conjugate base. Remember, these are the conjugate bases. And so the more stable the conjugate base, the more reactive the original acid was. So let's look at this reactivity up here at the very, very top. We can think of a proton transfer reaction here where we take a simple alkyne. Doesn't have to be acetylene, it can be any alkyne that we have, but it should be a terminal alkyne. That's where we get that pKa value, right? Because there's a hydrogen on one end of the carbon-carbon triple bond. And we get the acetylide ion, or the alkylide ion, right? The conjugate base here, where it's an sp hybridized carbon with a lone pair. Now, which base will work to do this, right? What do we have to remember? And what's really important to remember is low pKa to high pKa. Your pKa needs to be greater than 25, right? So looking at a couple of the bases we've seen before, hydroxide as a conjugate acid forms water. 15.7 for that pKa, not going to be good enough, right? Definitely not higher than 25. So that conjugate acid, hydroxide as a base, not reactive enough. When we think about any oxygen minus making the alcohol functional group, that ranges from 16 to 18 for its conjugate acid. Not good enough. Now think about N minus, nitrogen with 2 lone pairs and 2 hydrogens. That would be NH3 for its conjugate acid. Amines have a pKa of around 38. So NH2 minus 1, this is usually called amide. The amide ion is a reactive enough base because we see the conjugate acid there, NH3, is stable, and it's more stable in terms of the pKa, is higher than the original acid. Hydride, H minus 1, will react to form H2 as the conjugate acid. pKa there is 35, again, strong enough base. Butyl lithium, I wanted to present this one because it's seen sometimes in the textbooks. Remember, anytime you see lithium, sodium, potassium, anytime you see that group 1 metal, think about it being an ionic bond with whatever it's attached to. So butyl lithium is an sp3 carbon with a negative charge, very reactive, but still able to form. We'll see how that forms a little bit later in our discussions. Butyl lithium forms an alkane, pKa of 50 there. The last one that I wanted to talk about and present to you is LDA, lithium diisopropylamine, usually again with a coordinating lithium cation. And again, it's just another specific amide ion or amide ion. It forms that amine specifically, which is around 38 pKa. So all of these bases will work. We're just got to use something a little bit more reactive than what we have used before. Our bases of hydroxide or any oxygen minus will not work because they are not reactive enough. So we can see this chart in our textbook is a good representation of what will deprotonate that terminal alkyne. H minuses, N minuses, and C minuses will all be able to deprotonate that alkyne. The oxygen minuses will not be able to deprotonate. All right, preparation of alkynes come from a double elimination reaction. We've already gone through the E2 mechanism, but it is a concerted mechanism. And what happens here is that we can identify there are 2 hydrogens and 2 leaving groups. Now, if the 2 leaving groups are on the same exact alpha carbon, this is called a geminal dihalide. Sodium amide, or NaNH2, any of the previous bases we saw, can perform a double elimination reaction. Now, what this looks like is a triple bond forms in between alpha and beta. Notice there's another hydrogen on alpha. That's why we see a terminal alkyne forming. After step number 1, though, what happens is we actually can't stop. When a terminal alkyne is forming and you're using that strong reactive base to do an elimination, you also will do a proton transfer. Hence, that final step of the water workup, step number 2 there, to put the proton back on, right? So it's being able to isolate the idea that not only will sodium amide or our reactive bases do double elimination, but there's also the ability to proton transfer at the end. And so if you have a terminal alkyne, you will need to do a water workup as a secondary step there. This usually throws students off, and I usually don't use this as a abbreviation here, but I wanted to present it just in case you're using some other forms of videos or techniques. Writing excess. First time I saw that, I thought I was thinking extra small. Excess, extra sodium amide. You don't need to write that. I'll assume that it's there. You can't stop sodium amide from doing the double elimination, as well as doing the proton transfer if you have a terminal alkyne. So don't think just writing one equivalent or one molecule there is going to stop you from doing that double elimination or proton transfer. But it has been written before in textbooks and in other resources. So I wanted to present it. You can write out EXCESS as well for excess, or just X and S, the 2 letters. So our organic chemistry shorthand, if you will. Vicinal dihalide can be used as well, where we have 1 halogen on alpha, 1 halogen on beta. We also have a hydrogen each on alpha and beta. Again, this would make the terminal alkyne that then we would want to have that water workup for. So we can see H2O is used. We'll practice in class utilizing these preparation techniques of alkynes. First reaction classification that we're going to get to is catalytic hydrogenation, adding H2 across that double bond or that triple bond. The first one that we're going to see is adding a reaction reagent that we have seen before, H2 PDC. You could think platinum, you could think nickel, any of those reactive catalysts. And what that will do is it will add 4 hydrogens across that triple bond. It will go straight to the alkane. There's no stopping at any of the intermediate steps. That reaction is catalytic with a very strong catalyst, palladium on carbon, or a platinum catalyst or a nickel catalyst will take you all the way forward. Now, say you wanted to do that same concerted reaction that we saw in chapter 8, but you wanted to stop at the halfway point. You wanted to stop here at the cis alkene. Now, remember, hydrogenation in chapter 8, hydrogenation of an alkene using H2 PDC or platinum or nickel, added concerted, added in that cis or syn addition. Same mechanism here, where we can take H2 and add it to that triple bond, but we'll stop here at the alkene if you use a less reactive catalyst. So if we use this with Lindlar's catalyst, Lindlar's catalyst is a poisoned catalyst. Usually it's a palladium on carbon catalyst that's impregnated with calcium carbonate and quinoline and some other things to make it less reactive, to have less reactivity points. But all we would need to be able to know is this is a poisoned catalyst. So less reactive, poison catalyst, right? Another one that you could see out there is nickel boron catalyst. That's an alternate right here. Instead of saying Lindlar, you can also say Ni2B for that nickel boron catalyst that is less reactive. Notice nickel is the reactive catalyst in A. In the straight up catalytic hydrogenation we saw in previous chapters, we can poison that catalyst by impregnating it with boron as well, and therefore it makes it less reactive. And so we'll stop at the alkene. Now, just because we love our ability to have multiple options, what if we wanted the trans alkene? Well, you can't use catalytic hydrogenation with H2. It just won't work. Instead, what we are going to use is something called the dissolving metal reduction. And in the dissolving metal reduction, we are going to be utilizing a reactive solid metal, sodium. Notice sodium here is not positively charged. It's not an ion. It is the sodium metal that has one electron in its valence. NH3 will be utilized for our hydrogen source, so not H2. We will use ammonia. And this reaction goes through a very unique mechanism. We're going to walk through it right now. So this is for the dissolving metal reduction. I want you to be able to walk through this and know this mechanism because I feel like it's a very good introduction to our curved arrows of both single-headed and double-headed arrows. Just as a quick overview before we dive into this, we've been using double-headed arrows, right? 2 electrons moving at a time. What we are going to see in this reaction because of that sodium metal is our 1 electron at a time fishhook. Notice that fishhook right up here. The fishhook arrow is describing 1 electron moving at a time versus the double-headed, which is 2 electrons. So the first thing that we have here, and I'm just going to kind of redraw that 1 electron a little bit bigger. What we are going to see is that sodium will donate its electron to be paired with 1 electron from one of the pi bonds. It doesn't matter which pi bond you're starting to show, come out, and those 2 electrons are going to come together on one of the carbons. There are 2 electrons in a pi bond, however, so that means that the 1 extra electron has to be dumped on the other carbon. I'm going to name these carbon 1 and carbon 2. Carbon number 1 here is getting to become an anion. Carbon number 2 is a radical. So we have what we call a radical anion intermediate. Notice carbon 1 has a negative charge and carbon number 2 is neutral. Radicals are neutral, but they are reactive because there is a missing octet. Anions is that carbon has its octet, but it has an extra electron, namely from that lone pair. This is where the trans intermediate starts to form. We form an intermediate that is more stable, and we know trans is more stable than cis. And so that's where we can see that trans reduces the steric hindrance, and this mechanism is helping explain why we see trans as the product. Then we do a proton transfer with the ammonia, and we add on that first hydrogen. Notice we still have our radical here. We now have a radical intermediate, doesn't have a formal charge, but we still get to then keep going. We'll repeat this process again. Sodium metal will come and it will add itself with that one lone electron to become an anion. That anion then will do a proton transfer to pick up the second proton, right? So the trans adoption happens right in that very first step, and we see a merging of both fishhook and double-headed arrows here. So be very careful with this mechanism, noting that radicals and anions do not have any rearrangement. This isn't a carbocation ability to rearrange, right? So there's no movement of those electrons across or around the molecule. They are located and stationary, local on carbons number 1 and 2. And we do see that we have a leftover pi bond, right? Only one pi bond will react with our dissolving metal reduction, not both. All right, so variety of different reactions here. The alkyne can go straight to the alkane with an old reaction that we saw, H2 and a reactive catalyst. If we wanted to stop at the cis, we would have to use some sort of poisoned catalyst with that H2 reagent so that we did syn addition like before, but stopped at the alkene. If for some reason we want the transalkene, then we would go ahead and use the dissolving metal reduction, which is an anti-addition mechanism. Any of those alkenes can be taken forward with H2 platinum or palladium on carbon or nickel to become the alkane.